Hi, it's Mr. Duffy. Welcome to physics. Today our lesson is on projectile motion, specifically horizontally launched projectiles. Projectile motion is a great example of two-dimensional motion, which again was our previous unit, so we're going to continue on with that topic, talking about projectile motion. In this lesson again, we're going to be focusing on objects that move horizontally as well as vertically at again, the same time, which would be two-dimensional motion. Let's go ahead and get started. Lots of great examples of projectiles in everyday life. For example, I have this picture of a ball being tossed in there and it coming back down. Again, that's a great example of a projectile. It's not the only example, and again, like I said in the introduction, we're only going to be focusing today's lesson on horizontally launched projectiles. Objects that again are starting at the top of their motion, being falling to the ground. But again, projectile motion is any motion that follows a curved path. So objects that follow a curved path we would consider projectile motion. Here's a great example of a girl hitting a soccer ball off her head. So again, it's a nice parabolic path. Soccer ball, again, air resistance versus not air resistance, but again, it's a good example of projectile motion. Now, this also does bring up the point that a lot of our problems that we're going to be solving for today in real life are not going to get the same answers because of air resistance. Once we start talking about forces in motion and so forth, we can apply forces to projectile motion as well, including air resistance. But for right now, we're just ignoring that concept. So projectile motion is any object that follows a curved path. And again, it is an example of two-dimensional motion. So basically, again, it's an object moving in two directions at the same time, horizontally and vertically. So again, horizontally it would be left-right or east-west, and vertically it would be up-down, north-south. We're going to, again, just be focusing, again, the object's going to be moving left or right in our lesson today, but again, they're only going to be falling down. So again, they're still doing two things at once, but again, we're only going to be falling down. They're going to be up and down motion. Okay, so one of the most important things from today's lesson is to realize that the horizontal component, the left and right portion, is different and totally independent of the vertical portion. Really, it's kind of like we're solving two separate problems and then kind of like merging them together. So again, we've got the horizontal portion totally independent of the vertical component of its motion. How it's moving left and right does not affect how it's moving up and down. So when I say again how it's moving left and right, how is it moving left and right? Well, basically again, that's the object moving across the surface, again, horizontally, and gravity doesn't affect its motion. It is not accelerating. It is moving at a constant velocity. The equation for constant velocity is velocity equals distance over time or displacement over time. But again, since it's going to be moving, it's not going to be changing its motion, it's just going to be moving in one direction. Distance and displacement will be the same. So again, velocity equals just distance over time. Constant, always continuing its motion at the same rate every second. However, on the vertical component, it is accelerating. Gravity is accelerating this object. The object would be considered to be in free fall because the only thing causing a change in its motion would be gravity. So if that's the case, we have some of our other kinematic equations that would involve acceleration. We just have to choose which one we're going to use based on what information they give me in the problem, or again, maybe what I would be able to solve from this horizontal component. So again, just depends what we have to use based on each individual problem, but again, we have these kinematic equations to be using, which we've learned before when we talked about one-dimensional motion. So again, objects in free fall, no air resistance, using our kinematic acceleration question. So let's take a look at an example problem. Again, a horizontally launched projectile. Here we've got a person kicking a rock off a bridge. So this is the Royal Gorge Bridge in Colorado. It rises 321 meters above the Arkansas River. Suppose you kick a rock horizontally off the bridge. The magnitude of the rock's displacement is 45 meters. So again, it splashes in the water 45 meters below the bridge. How fast did that kick the rock? Okay. So again, what I would suggest is with any kinematic equation, or again, when we talked about one-dimensional problems earlier, list what's given, and then draw a diagram. Well, the diagram's already drawn for us, but we do need to list what's given and what information we have. So the first thing that's given to us is the displacement in the y direction. and that would be negative 321 meters, because again, it's falling down, so we have, again, a negative direction. Then the next thing that's given to us is the horizontal displacement. So that would be the displacement in the x direction. So I'll do that, x direction, y direction. So the displacement in the x direction is 45 meters. And that would be positive because it's to the right. Okay. Well, it doesn't really tell us if it's the left or the right, but again, we're just going to assume it's positive. So if other information that, again, that's not necessarily given to us is that it is falling down, so we would know the acceleration. The acceleration is negative 9.81 meters per second squared because it's gravity. Gravity is what is accelerating it down. Now, what we're looking for is the velocity that it was kicked off the bridge in the x direction. That's what the problem is asking for. But we also know that it was not kicked, it was kicked horizontally, so the velocity in the y direction initially is 0 meters per second. So again, that's just something important to know. It's not going to affect, well, it will affect our equations a little bit later on, but again, that was no initial velocity in the y direction. The initial velocity in the x direction is what we're looking for. So I think this is enough information to actually, again, solve this problem. It's going to involve, basically, we need to find time. So a lot of our problems are going to be come down to how much time was this ball in the air. So if we take a look at, again, the equations that I kind of gave you earlier, the horizontal component of its motion, the velocity in the x direction, equals the displacement over the time. Now, like I said, where it's going to come down to is really time. We know that it moved 45 meters in the x direction. Okay, that was given to us in the problem. But we don't know the time that it was in there. So again, I can't really solve this problem yet because I don't have the time. So let's take a look at the vertical component of its motion. The vertical component of its motion, I know the displacement that it moved, I know the acceleration, I know the initial velocity. And so again, if I kind of like go back to the previous problem, if I have that piece of information, what equation can I use? Well, hopefully you realize it's the middle one. The displacement equals the velocity initial times time plus half gt squared. Again, I have all that information except for time, so that's going to allow me to solve for time, and once I do that, then I can plug it into the horizontal component and solve the answer. So let me write that again here. The displacement, or the distance, equals the velocity initial times time plus half gt squared, which again, g is just gravity. Now, what's going to happen here is that the velocity initial in the y direction is 0, so that part of the equation is going to cancel out. We don't have to do anything with that. And again, all other pieces of information we have. So the displacement is negative 321 meters, half of negative 9.81 times t squared. See that we only have one variable to solve for, and that's t, and we can definitely do that. So half of negative 9.1 is negative 4.905. T squared, negative 321. I'm going to divide both sides by negative 4.905. So negative 321 divided by negative 4.905 is going to be, and again, that'll come out to be positive because it's negative divided by negative. We've got 65.4. Now, that is not t, that's not their time, that is t squared. So we need to take the square root of both sides to get it to be just t. If I take the square root of 65.4, I get a time of 8 seconds, 8.1 seconds. Oh, that's not my final answer, but again, sorry, I shouldn't circle that. But it is going to allow us to solve for the velocity. So that time that it's in the air as it's falling down is equal to the time that it takes to go left and right. And so that time is exactly the same over here, and so I have time of 8.1 seconds. So the velocity in the x direction can now be solved by taking 45 divided by 8.1, and I get a horizontal velocity of 5.6 meters per second. 5.5 meters, really. There is your final answer. So, again, hopefully you can kind of see that we can solve these problems again separately. So they are intertwined, but again, they can be solved differently based on the vertical component and the horizontal component. We used the vertical component's information to be able to solve for time, and then we were able to use that in the horizontal component to actually solve for, again, the distance or the velocity that it was going in the horizontal. So again, just different ways of solving problems depending on what they give you. So hopefully this makes a little bit more sense as to what horizontally launched projectiles motion is like, and thank you for watching.